Now let's do the Minkowski analog of what we were doing with the parallel lines before. The interpretation here is that a train is passing through a station. So let me describe most of the stuff in the diagram in terms of that. The black lines are the left and right ends of the train station. And we've drawn them in such a way that we're kind of privileging the station master's point of view by drawing those straight up and down. But that's not really essential. And then here is a rest space. This is the station. Actually, I should make that in black. This is the space according to the station. That's orthogonal to his world lines. Okay, and then there's the left-hand end and the right-hand end of a train. And you can see because those are slanted, the train is moving relative to the station. And then here is the train space. It's called the rest space. That if you're at rest relative to the train, you think this is pure space direction and this is pure time direction. I draw one null line. We're not going to use light at all here, but just to make sure that you can see that these guys should look at equal angles to the null line. Okay, so here's the interesting fact that the station master, I'm just going to abbreviate that as S, he says that the station has length 100 meters and the train has length 100 meters. They fits exactly into the station. But the claim is that the train conductor disagrees. He says the station is 50 meters and the train is 200 meters long, and so it's 4 times as long. So are either of these people right? They can't both be right. So here's T and S disagreeing. And what is the real situation? Okay, and what's going on is some of these measurements are exactly the analogs of the silly incorrect measurements in Euclidean case. So here's what's going on. What is true is that the distance between A and B, the Minkowski magnitude of the vector AB, is equal to 100 meters. Now that is both a correct measurement of one thing and an incorrect measurement of another. Let's look at it. The station master's world lines are like this, and the AB segment is on a perpendicular to the station master's world lines, the S space. So that is the correct length of the station because it's measured by the station master who's at rest relative to the station. You can't measure a length if you're moving relative to something. Okay, not going to get the right answer. So it's also the incorrect length of the train because it's true that the left end of the train and the right end of the train were at the left end of the station and the right end of the station respectively, but not at instants that are simultaneous according to the train. Okay, so let's think about this for a second. Let's not worry about the relativity of simultaneity for a second, but let's just think, if I'm measuring a moving object and I purposely measure the location along a track of that moving of one end of the moving object, and then at a different time measure the location of the other end of the moving object, nobody's going to believe me in thinking that's going to be the correct length of the moving object because it's moved in the interim. Okay. The tricky thing, of course, is that people can disagree about the issue of what's simultaneous. The station master says, I don't think I'm falling into that incredibly obvious error of marking the positions of a moving object at 2 different times because that's the same time. But the thing is, that's relative. That would be true for the station because it's not moving. But for a moving object, you have to be much more careful because the right version of simultaneity is different. That's this red line. Okay, so this is an incorrect measurement, and it's exactly analogous to taking these green lines in Euclidean geometry and saying that this thing is the distance between those 2 lines. It's not, because it's not orthogonal to the lines. It's just the wrong definition. Okay, now what about the train conductor? Is he correct? Well, one of these is correct. You can probably guess which one it is. I'm going to show to you that with the right choice of the velocity of the train, this really could be a correct measurement of the train. And then this is exactly an incorrect measurement of the station. So let's actually do that. So this is one of the numerical things we're starting with, and here's the situation that makes these numbers work out. It's if the velocity, v, is root 3 over 2 times the speed of light, so about 87% of the speed of light. Okay, so what I'm going to do with that is I'm going to put in two vectors. The vector v comma 1 is then going to be along this world line of the train. In terms of, we're going to use the station master's coordinates, but then we're going to use the fact that this vector, if I go 1 unit in time, I'm going to go v units in space. That's what it means to have relative velocity root 3 over 2 relative to the station. Okay? And then that means, how do I get the perp? It's going to be very useful to get the perp here and project onto this direction in a minute. Well, that's easy. To get the perp in Euclidean geometry, you switch the coordinates and put a minus sign in. In Minkowski geometry, you just switch the coordinates. 1 comma v. And you can see if you take the dot product, it's going to get v minus v equals 0. Oh, that's the Minkowski scalar product. So let's call that vector w. Okay, so now we're going to use little projections to get what's going on here. Let's look at the vector AC. AC is a very interesting vector because that's going to be something whose magnitude is the correct length of the train as measured by the train itself. Because it might not look like it, but this angle here at C, the angle ACB right here, is a right angle. Because this T space is drawn to be Minkowski orthogonal to the green lines, the left and right end of the train, the world lines of the train. So if we project, what we're going to do is we're going to find the length of that by projecting a known vector perpendicular to this guy. So AB, so we really want to find the magnitude of this guy. So what we're going to do is we're going to project AB, which has a known length, onto the direction W. Okay, so here's W, and I've got a vector that's definitely not perpendicular to the green, but then I'm going to project it to this guy. And I know this doesn't look like a right angle right here, but it is. Okay, so we have a formula for that. So the magnitude of that projected vector is going to be the absolute value of AB, the scalar product W, over the magnitude of W. Okay, so that's a nice use of projections. Okay, I'm going to have to erase that, but remember, the 50 and 200 will come out of our calculations, and we'll check those. Okay, so let's just calculate that out. Okay, AB is 100 comma 0, and W is 1 comma V. Eventually I'll put in the explicit numerical value for V in a minute, but I want to show you something in terms of the variable V in a minute. And then divided by the magnitude of 1 comma V, which is just the square root of 1 minus V squared. Because remember, it's not A squared plus B squared, it's A squared minus B squared. That's the Minkowski magnitude. And that quantity is going to be very important. So up here it's very simple, it's just 100, because the 0 doesn't pair. And I get something that's going to show up a lot from now on. This quantity 1 over 1 minus V squared, 1 over the square root of 1 minus V squared, is called gamma. And so that's 100 times gamma. So gamma is a function of, when you have two objects moving at a relative velocity v, gamma is this quantity 1 over the square root of 1 minus V squared. And it just shows up all over. Because basically, I mean, the way I think about it is we're using projections. Projections involve dividing by a Minkowski magnitude, and that's where it comes from. Okay, now what is this numerically? Given that V is root 3 over 2, so gamma is 1 over the square root of 1 minus the square of this, which is 3/4, or 1 minus the square root of 1/4, or 1 over rather, and so that's going to be 2. Okay, so gamma is always this factor that's bigger than, greater than or equal to 1, and so the magnitude of AC, which is the correct length of the train as measured by the train conductor, is 200 meters. Ta-da. So the train really is longer than the station. The train, the station master thought it fit exactly into the station because he's incorrectly measuring that length. He's not using two simultaneous events. So this is often known as, this is originally discovered by Lorentz, that this seemed to make electrodynamics work, basically. And it's expressed as Lorentz contraction. And the very bad way it's often phrased is moving objects are contracted. That somehow, and the impression people get is that the train is moving, therefore it gets shorter. That's a horribly bad way to think about it, because for a couple reasons. There's no such thing as motion in an absolute sense in relativity. That's the whole point of calling it relativity. There's no such thing as a moving object. There's just relative motion. Okay. The other thing is that it seems to make it, again, a symmetrical situation. It seems to be paradoxical. If the train is the one that's moving, then maybe, yeah, okay, maybe you could picture it as being shrunk from 200 meters to 100 meters. But wait a minute. According to the train conductor, what if isn't the station moving? Shouldn't he be shrunk? So which one should you pick? Is it the train that's shrunk or the station that's shrunk? And you seem to get a paradoxical situation. The real way to think about it is that there's just a lot of incorrect measurements of length floating around. And back to this idea that if you use two different times to mark the position of a moving object and then measure the distance between those, it's a ridiculously bad way to measure a length. Also, the analogy to Euclidean geometry is good, that this segment here is absolutely the wrong thing to pick to measure the distance between these two lines. Admitted, if you've never done any Minkowski geometry, telling somebody that this is the right segment to pick seems a little weird. But if you know that this segment is really orthogonal to the green line, then it does make more sense. Now, what about AD here? Let's finish up by looking at AD. That is another incorrect measurement. That would be if the train conductor uses his notion of simultaneity to measure the length of the station. And that's just as bad as the train conductor's mistake when he thought that the train was 100 meters. And that there is some symmetry here, and we'll see that. Okay? So one way to do that is simply that we actually have we can just pull out the coordinates for AD. It's the magnitude of, this is a vector that's clearly going 100 meters in the station's x direction, and then it's along the vector 1v. So actually what it is, it's really just 100 times 1 comma v. Because that gets it in the right direction, in this space direction for the train, and then it gets the right x coordinate, the 100. Okay, so the 100 comes out, surprise, surprise, and I get magnitude of 1 comma v. Oh, hey, that's square root of 1 minus v squared. That's 1 over gamma. And so you get 50 meters, because the gamma is still there, it's the 2. Okay. And so that is where that kind of symmetry goes in. It's true that according to the train conductor, he sees what is really a 100-meter station, he sees it contracted to be 50 meters. And it's not a contradiction. It's not that the train is bigger than the station and the station is bigger than the train or something like that. It's that they're comparing apples and oranges. There's two correct measurements, which have to be made by the people themselves. The train has to measure the train, the station has to measure the station. And then there's these two incorrect measurements. The AB, thought of as a measurement of the train, the green, which is incorrect, and the AD thought as a measurement of the station, which is also incorrect. So again, I really love how looking at the Euclidean version tells us some of these things are just obviously wrong. And there's good physical reasons why they're wrong as well, but there's nice geometrical reasons why they're wrong. Okay. And that's a good place to stop this video.